Hello students, this is lesson U1A004a. By the end of the lesson, you should be able to say I can factor binomial trinomials with a leading coefficient of 1. So this is actually part 2 of a video going over the exercise U1A004a. In part 1 of the video, we went over these examples over here where we were able to find the GCF and factor out that expression, factor out that term, and rewrite the expression. We're going to attempt that for the lower half of that exercise, which is this right here. So what we're going to do, okay, let's take a look at question number 13 first, okay? So what we're doing here is we're trying to rewrite this into a factored form. So if you look at this, notice right now, you have 3 terms here, but there's no GCF. Is this thing factorable? As a matter of fact, it is, because if you look at this, this is actually a quadratic equation, and if you recall, when to undo the multiplication, it should look something like this, where we have 2 binomials multiplied by one another. So if you look at this, okay, immediately I recognize there has to be a k value here and a k value there. Then the trick, if you want to even call it that, right, is we want to focus our attention on this number right here, 90. And we recognize that these two numbers over here should multiply to that number. However, we have to pick wisely though, right? The numbers that we pick, okay, over here, okay, needs to, when we FOIL this back out, okay, these two numbers multiply together and these two multiply together, and combined they get the number in the middle. Which is why when you are factoring, the technique that your teacher in the past have told you was you want to consider, okay, 2 numbers that multiply to the last number but add to the middle number. Can you think of a number that multiply to the last number but add to the middle number? Of course you can. It's 9 and 10, right? So in other words, this product, okay, that will lead to that trinomial would be plus 10 and plus 9. So we factored that trinomial. Well, let's attempt that again, this time for number 11. So we're working a little backwards here. So we're factoring, okay? So again, we are looking for 2 pairs of binomials when multiplied together, giving us m squared minus 14m plus 48. Immediately I know that m and m is supposed to be here because m times m gives me m squared. Again, we want to look for 2 numbers that multiply to 48, while at the same time add to negative 14. So we have a couple of options here. We know that 6 and 8 definitely gets us positive 48, right? However, we want the middle number to add to negative 14. Is there another way that we can multiply 2 numbers together to get us positive 48, yet at the same time when we add those 2 factors giving us negative 14? As a matter of fact, yes, of course. So the 2 numbers would be minus 6 and minus 8. Let's take a look at another question. Let's take a look at number 15 here. So looking at this, I immediately see that this number over here, okay, the leading coefficient is not 1. However, upon closer inspection, these numbers, okay, appear to have a GCF of 5. And you know what? I'm going to factor out a negative 5 because having the leading coefficient here be positive 1, I don't know if you guys felt this, okay, it did feel like easier, quote unquote, right? So I want to factor out a negative 5. So if I factor out a negative 5, I want to be left with p squared minus 11p plus 30. All right? So what 2 numbers, okay, so again, I want to factor out this completely. So I know immediately that I'm supposed to have a p and p there, okay? What numbers multiply to 30 while at the same time add to negative 11? Well, that would be negative 5 and negative 6. Isn't that wonderful, right? So easy. Okay, so let's take a look at another one here. I have 2x squared plus 10x minus 28. If I do that, that would be, there's a GCF of 2, of course. So it's 2 times x squared plus 5x minus 14. Are there two numbers that multiply to negative 14 while at the same time add to positive 5? Right? Actually, yeah. That would be 7 and 2, right? Positive 7 and negative 2. You know, we could have also done the flip side of this. It could have also been minus and plus, but upon closer inspection, why would that not be the case? Well, that's because if I multiply negative 7 and x together, I'll get negative 7x. And x and positive 2, I'll get positive 2x. And add them together, I will not get positive 5x in the middle. So therefore, it cannot be this combination. It has to be positive 7 and minus 2. Let's move on to others, okay? So what happens if I have a binomial like this, where there's no middle term? Well, actually, you can think of it in this regard then, right? So, and you can think of this as 4m squared plus 0m minus 25. You can think of it like that. However, also upon closer inspection, can you see that this is actually a perfect square and that this is a perfect square? So what we end up with, this is actually a squared minus b squared. Do you remember this, right? And this, and how we were able to get a difference of squares is by two binomials multiplying together a plus b and a minus b. So if we follow this format, right, what would a and what would b look like? Well, it would look like this. It would be 2m plus 5 and 2m minus 5. If that was too much for you, okay, another way of thinking about it is, well, how can I get 4m squared here? I can get 4m squared by 2m and 2m, right? And then what numbers can I put in to get 25, to get negative 25? Well, one way is positive 5 and negative 5. And look, we've articulated and we end up in the same place, okay? All right, let's try another one. This one right here looks really tricky, doesn't it? Actually, this follows another pattern. And I want to point this out to you guys. If you look at this, you see 25r squared there and you see 9 there, right? Those are perfect squares, aren't they? Yeah, they are perfect squares. And actually, okay, if they are perfect squares, that should give you a hint as to what they look, as to the perfect square form. So if you remember, a plus b, quantity squared, becomes a squared plus 2ab plus b squared. Is this actually the case? If you look at this right now, right, can you see what a is? Right? If a squared is 25r squared, that is, a would have to be 5r. If you look at b squared, right, b squared is 9, so that would make b equal to 3 then, right? And because I have a plus here, right, I know that I'm supposed to have a plus there. So I have 5r plus 3 quantity squared. Will I be able to get 30 here in the middle? Let's see here, 2 times 5r times 3. Yes, indeed, it does. So this is an example of factoring perfect squares. I have 5r plus 3 quantity squared. Let's take a look at the next one here. 9m squared and 4. Those are perfect squares, aren't they? Yes, they are. So I actually can have a perfect square of this form. This is a squared minus 2ab plus b squared. Well, in this case then, a is equal to, let's look at this, 3m, right? And b over here is equal to 2. So actually, this is going to be 3m minus 2. Will we actually get negative 12 in the middle? Let's see here. Let's see. 2 times 3m, 2 times 3m, that's 6m, times 2, yes indeed, I will get 12. Let's try one last one here. So can you spot which form is it going to be? Is it a plus b squared or a minus b squared according to what we just discussed? Right? I have 9k squared and I have 1, right? Those are perfect squares. So this will be 3k plus 1 quantity squared. And there you go.